Welcome back to DeepVisus, where vision meets depth. I'm your host, and today we're pulling back the curtain on the exciting and sometimes messy process of actually building intelligent systems. We've explored the grand theories and the core principles, and now it's time to see how they come to life in the lab. Our deep dive today covers chapters 16 and 17 from Part 5 of Understanding Intelligence by Rolf Pfeifer and Scheier, a section aptly titled Design and Evaluation. Last time, we delved into the driving forces of learning, like the value principle, and how even something as complex as memory is shaped by an agent's active engagement with its environment. But once we have these principles, how do we translate them into a working robot or a complex simulation? And once we've built it, how do we know if it's truly intelligent, or if our design is any good? This leads us to our central question for today. How do we effectively design and evaluate intelligent agents to truly understand the nature of intelligence itself? Chapter 16, Agent Design Considerations, throws us right into the thick of it. Designing an intelligent agent is far from a simple step-by-step process. It's a creative, often chaotic journey that involves balancing countless factors simultaneously. Think of it as bridging the gap between what the agent should do, its functional requirements, and how it's actually built, its physical design. One of the first crucial steps is defining the ecological niche. This is the specific environment where our agent will operate. Unlike universal computer programs, a real-world agent is always designed for a particular context. A robot built for a flat office floor will look very different from one designed for the rocky surface of Mars. Exploiting the unique features of that niche can greatly simplify the design. For example, if an office floor is flat, a camera can quickly estimate distances based on how high objects appear in its view. Next, we define the desired behaviors and tasks. What exactly should our agent accomplish? Should it sort objects, collect trash, or navigate a complex maze? This choice directly impacts the agent's low-level specifications, the nitty-gritty details of its physical setup, like its body shape, the types of sensors it has, and its motor capabilities. For instance, if our robot needs to pick up delicate objects, it will need a very different gripper than one designed to push heavy boxes. The chapter then dives into the practical choices. Sensors. Do we use simple infrared sensors for basic obstacle avoidance, or high-resolution cameras for detailed object recognition? The choice depends on the task and the environment. The book emphasizes that redundancy, having overlapping information from different sensor types, isn't just for backup. It's crucial for learning and generating diverse behaviors. Motor systems. Should our robot roll on wheels or walk on legs? Wheels are often simpler and cheaper, while legs are better for rough terrain. And how will it manipulate objects? Simple hooks, grippers, or complex multi-fingered hands? The more complex the motor system, the harder it is to design and control. A control architecture. This is the brain that connects sensors to motors. We've seen various approaches like the subsumption architecture or extended Bratenberg architectures. The key is to choose an architecture that supports parallel, loosely coupled processes, allowing for emergent, adaptive behavior. Finally, Chapter 16 touches on a fascinating cutting-edge area, neuromorphic engineering. This involves building specialized computer chips that mimic the way biological brains work, using analog circuits instead of traditional digital processors. These chips can be incredibly energy efficient and directly exploit the physics of computation, offering a glimpse into a future where robots might operate on principles closer to natural intelligence. Once we've designed and built our agent, Chapter 17, Evaluation, tackles the crucial question: how do we know if it's any good? Simply saying it works isn't enough for scientific understanding. Evaluation is always tied to our research goals. Are we building a robot for a specific task, studying general principles of intelligence, or modeling a natural system like an animal or human? The chapter outlines key evaluation criteria. A task performance. Does the agent successfully complete its assigned tasks? How fast, how accurately, how efficiently? A comparison with natural agents. If we're modeling a natural system, how well does our agent's behavior match the real thing? A compliance with design principles. Does our agent's design adhere to the principles of embodied cognitive science, like cheap design or sensory-motor coordination. This speaks to the internal validity of our model. A heuristic value. Does our agent lead to new ideas, insights, or ways of thinking about intelligence? This is especially important for fundamental research. A cost benefit. Is the effort and resources invested worthwhile compared to the insights gained? The book stresses the importance of systematic experiments. Unlike traditional AI, where you might just inspect the code, the emergent, often probabilistic behavior of embodied agents means we need to run many trials and use statistical methods to draw reliable conclusions. We record not just the agent's external trajectories, where it moves, but also its internal dynamics, like sensor readings, motor speeds, and neural network activations. This unique ability to observe both inside and out is a huge advantage over studying natural systems. A significant challenge in evaluation is the underdetermination problem. Multiple different models or designs can sometimes produce the exact same external behavior. This means that just because a robot acts intelligent, it doesn't mean its internal workings are the same as a human's. To address this, we rely on those additional criteria like internal validity, parsimony, simplicity, and heuristic value. So, to answer our guiding question, effectively designing and evaluating intelligent agents involves a nonlinear, creative process that integrates the agent's ecological niche, desired behaviors, and physical design. We aim for emergent intelligence by leveraging principles of sensor-motor coordination, cheap design, and parallel processes. And we evaluate these agents not just by their performance, but by their reliability, their internal consistency with our theories, and most importantly, their heuristic value, the new questions and insights they spark about the very nature of intelligence. And with that, we conclude our exploration of Part 5 of Understanding Intelligence. Join us next time on DeepVisus as we embark on the final part of our journey, looking towards the future directions of brain, mind, and intelligence, and uncovering what lies ahead in this endlessly fascinating field. You won't want to miss it.